Hello students, welcome back. Let's go back to section 2 of this notebook. I marked it as review, so if you went this topic, section 5 of lesson 14 already, and if you feel comfortable, then you don't really have to do this. But if you skip that topic in lesson 14, or you did but you want to repeat it with a little bit different viewpoint, okay, this may be for you. Okay, we completed all these and then ended up with this conclusion. And from this point on, I'm going to use this. Okay, what kind of problems are there? Okay, here's a system. And we want to use this formula. There's a bit of a problem here, which is just a small problem. These are written in terms of matrices. This one, not yet. So looks like we'll have to get the matrix expression done. Okay, no problem there. So y1, y2, and then those are derivatives. And then that's equal to, and then this part, we have -1, 2, -3, 4, and then we have y1, y2. That took care of this part, homogeneous part. Now the non-homogeneous part, we have e to the t power, and then minus 2e to the t power, and that'll complete the ODE, or the system of the ODE. Now the initial condition, y1 of 0 and y2 of 0, we have 1, 1. Is that clear to everybody? Here's the IC, and the IC is here. And then here's the system, and there you go. Feel comfortable? This is your A, that's your capital Y, that's your capital F, and here's your Y star. And one more thing, here in this formula, let's see, we're beginning from 0, so we don't need this arbitrary t0. We just go back to 0. So t minus 0, so it's just okay to have just a times t, and then this integral goes from 0. Okay, some minimal adjustment. And let's consider this. Let's see, what do we have here? Obtain the matrix form. Okay, the repetition of something we just did. Feel comfortable? Okay, all right. Now let's solve the homogeneous equation. Basically, I want this. And then times y star, which is this multiplication. No big deal. But how do we find the matrix exponential? Oh boy, there goes the problem. And let's study that. Remember everybody, the key part is this matrix exponential. And remember, the matrix exponential is obtained by the Laplace inversion. Let me get the character here, excuse me. Si minus A. That's basically what we are up to. That will give me this matrix exponential here. And in the end, we just multiply by this, which is no big deal. Here's a big deal. So how do we handle it? Well, if you have multiple parentheses, the rule of thumb is start from the inside. So start from here, and then we're going to take the inverse. And then we'll have to take this Laplace inversion. But whenever you take the Laplace inversion, probably you'll have to take this decomposition by partial fraction. And that's going to be the computation intensive step. So here we go. Si minus A what is it? Let's do s minus I, s times I. So s times, what is I? 1001. Minus A, what is A? And A is here. And let's do that computation. Feel okay about this? Now, s times that, nobody will write like this. Everybody will jump to this one directly. S times I as this one directly. That's probably what everybody will do. All right, experienced students will jump actually directly from here to this step to tell the truth. Si minus A, so S minus this, so we have S minus of negative, so S plus. 0 minus 2, so sign change. 0 minus of negative 3, so sign change. And the S minus of this, so we get that. Basically, we need sign change for all these. And then we have S and S in the principal diagonal. That's how it works. Okay, this is Si minus A. And what I want is the inverse of this, right? So what I want is inverse of that. Okay, how do I find the inverse matrix of a 2 by 2 matrix? I hope everybody remembers this formula. A, B, C, D. This one is 1 over AD minus BC, the determinant. And then from this matrix here, we have to switch the principal diagonal. A goes to D, D goes to A, and then the other have sign change. And this is the inverse matrix formula that everybody must remember, for 2 by 2 at least, and let's apply that. 1 over AD minus BC. And then minus of that, so minus minus plus. That's what we get. And then in this matrix here, we have to switch the principal diagonal. A goes to D, D goes to A, and then change the sign for the other numbers. That's how we apply this inverse matrix formula. So we have the expression of this resolvent matrix. So we first calculated this, and then using that inverse matrix formula, we got this one's inverse. Looks like we need some further simplification here before applying this Laplace inversion. Looks like we have to go a little bit further. Let's copy and paste this thing here, and let's see what kind of simplification we can get. This part we can break apart. We're gonna get s squared minus 3s minus 4. Did I get it right? Did I break it up correctly? And then I have plus 6, so we're gonna get plus 2. Then this can be factored even further. Looks like this can be factored. That's s minus 1, s minus 2. Did I get it right? So I can slip in this to each entry here. If I do that, this is the matrix expression I'm gonna get. Let's see, s minus 4 divided by s minus 1, s minus 2. 2 divided by s minus 1, s minus 2. And then negative 3 over s minus 1, s minus 2. And finally this s plus 1. And that thing divided by s minus 1, s minus 2. Looks like everything is ready for the decomposition by partial fraction. You see, in order to decompose by partial fraction, the denominator has to be factored. And yes, we completed. And please note that everything here is proper rational expression. First degree over second degree, 0 degree over second degree, 0 degree over second degree, first degree over second degree. So we do not have the polynomial part coming out here. No quotient part there. Just remainder over the denominator. So the decomposition by partial fraction is going to be done in the usual fashion. So each entry will be of this form: a over s minus 1 plus b over s minus 2, kind of like that. And the coefficient here, a, b, will be appropriately changed for here, 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 and there. So maybe you can rewrite them as a11, b11, a12, b1, never mind. All these will be of this form if you do that computation correctly. Now, do you want to do that computation on your own right now? The decomposition by partial fraction? Be my guest. You can stop this playback and just go ahead. But then again, I don't want to. It's just tedious computation, elementary but tedious. But so here we go. I just used computer algebra system for that. We got everything, the same thing, and then the decomposition by partial fraction will turn out like this. And the mathematical command I use, as a matter of fact, is this one. And then this is what Mathematica spat out, and that's what I have adopted here in traditional form. Now that we have all those fractions, I can take the Laplace inversion. You see, look at this factor here. 3 over s minus 1, I'm just highlighting in blue. 3 is a coefficient, so we have 3. And then 1 over s minus 1, eigenvalue is 1. So look up this Laplace table in page 123. You're going to get e to the t power. That blue. Do you see this becoming that? Maybe I should highlight in bold so that you can see this in better. How about the next fraction here? Coefficient is negative 2, and then the fraction is 1 over s minus 2. Eigenvalue is 2, so we have e to the 2t power. If you look up that Laplace table, and indeed that's what we get. That's for the first entry, 1 entry. I'll have to repeat it for all 4 entries, and because of this denominator, the denominator is coming from the same determinant, AD minus BC, so they are the same, so we have to have same eigenvalues here. So e to the t and e to the 2t, there's nothing else. You have to get all those coefficients appropriately, but assuming you did all those, you're going to get the Laplace inversion like this, and that is the matrix exponential look for. We're almost done. If you multiply by the initial condition matrix, this one, you see, where's that? Yeah, this part, or this part here. Then you're going to be done, and here is the solution. The solution of the homogeneous part. It turns out, in this case, e to the t power, e to the t power. As for finding out this Laplace inversion method and e to the at power, well, that's something we did let's see, that's something we did in lesson 14 and partly in lesson 13 as well, depending upon how much review we are doing. So that took care of this. Okay, let's go to the particular solution here. It looks like we have to take another matrix exponential here, excuse me, and then matrix multiplication, and then integral. Oh, looks like another Laplace inversion. Oh my. But no, don't be intimidated. We got this, okay? Let's copy and paste. That's what we got in a previous step. We got it, and I don't need this color coding anymore, so let me keep everything in black. Okay, we got it here. And we want e to the t minus u power. How do we get that? All I have to do is to replace t by t minus u. I forgot a. So in this expression, which is for e to the at power, now I want e to the a t minus u power. So all I have to do here is to replace all these t's by t minus u expressions. I have to do this 4 times, which is right here. Which is right here. So from this expression here, we found out earlier, replace t by t minus u, and I have e to the a t minus u power. I don't need this any longer. And that's this part. So matrix multiplication, this e to the a t minus u power times f of u. Well, some brute force computation, I guess, and you're going to get something like this. So what is the formula here? We have to multiply this times that. And then f of t is given like this, e to the t power, negative 2 e to the t power. I want f of u, not t, so you have to replace those characters to u, which I did here. And then take this matrix multiplication here, and then you get the conclusion like this. Be careful here. T and u are mixed up. One of more common mistake here is to just use t's here. And once you make that mistake, it's going to be difficult to find out because there are t's as well. So which t is which t, and which t is correct t, and which t is mistake t, it's really hard to find out once you make that mistake. So f of u, make sure all these are u, and then here we have t minus u. Once that is all done, please check and then go ahead with the computation. And then we get this. Almost there. We got the integrand, so all you have to do now is to take the antiderivative, or more precisely speaking, the definite integral from t0, which is 0 to t. And here we go, 2 definite integrals. 2 fundamental theorem applications. And then we have these. That'll give me my red solution, the particular solution that we are after, this integral part. Was I too quick? Probably. That's because these are all elementary computations, tedious but elementary. So if you want to do this on your own, stop the playback and do some computation of your own. All right, we just got this red part, and then we previously got this blue part, so put those two together and add them up, and we have the desired solution. This is what we found out in the previous step, and this is something we found out in, well, just now. Step 2 we got this, step 3 we got that, so add them up. That's the conclusion, and that is step 4, adding those up, yh plus yp. And then, let's see, I have a little bit of time left, so let me explain you with this mathematical command what it does. That's y1, so I defined it here. And this is y2 down here, so I defined it here, down here, y1 and y2. And then these are the differential equations, so y1 prime, and then flip all these to the other side, and then got this expression, and then make Mathematica to simplify. You have to get 0 because these two are equal, and then flip all the right hand side to the left hand side, so equal to 0. And indeed, equal to 0 for the first line, equal to 0 for the second equation. That's how this command is working. All right, we completed one problem, and the other problems, well, we'll discuss those in a separate video. Let's stop here.